Okay, so to pick up where we left off in class, we were talking about the playing life of a sunshine radio. We said it was normally distributed with an average of 600 hours and a standard deviation of 100 hours. The one that we got to was the probability that a radio selected at random would last from 600 hours to 700 hours. So the probability is that area under the curve. To figure that out, you're going to normal CDF, and you're going from 600 to 700 with an average of 600 and a standard deviation of 100. Going to grab your calculator, and you're going here down to CDF. Your lower is going to be your 600. Your upper is going to be your 700, and then your average is 6, and your standard deviation is 100. So 0.341, so we're going to go 34.134%. Then it says, what's the likelihood that a sunshine radio will only last 450 hours? So 450 hours is going to be that it lasts in here. And this is when we talked about negative infinity. So I'm going to go normal CDF, and we talked about the fact that you could start at 0 because it can't have negative battery hours. And that's fine, but you could also do the negative infinity. I'm going to 450 with my standard deviation, or with my mean and my standard deviation. And we typed that in and got 6.681%. And I think that's where we left off. So just remembering that normal CDF is your lower, your upper, your mu, and your standard deviation, your sigma. What's the likelihood that a sunshine radio will last more than 825 hours? So I'm here. And when you do this, you should make sure that your answers make sense. Like, I knew that this wedge over here was going to be small, and it is. It's less than 7%. So if I'm looking at this guy, he should be even smaller. So if you get something like, I don't know, 87%, something's wrong. So make sure it makes sense. So I'm going to normal CDF, and let me clarify for tests. I have to see this right here. Have to. You cannot just magically have a number. You have to show me the normal CDF. I'm going from 825. Now this one, I'm not going to 900 because you know that there's some random freak radio out there that's going to last forever. So I am going to go to positive infinity. Standard deviation, or mean and standard deviation. And I go type this one in, 825, 1, E99. So this is 1.222%. The Sunshine Stereo cassette deck life is normally distributed with a mean of 2.3 years and a standard deviation of 0.4 years. So this is only going to last us an average of 2.3 years. What's the probability that a cassette deck will break down during the guarantee period of 2 years? All right, let's state what we got. I've got a mean of 2.3 years. Always use units of measurement. I've got a standard deviation of 0.4 years. I want that it will break down during the guarantee period of 2 years. Okay, so is that greater than 2 years, or is that less than 2 years? Well, the guarantee is from 0 to 2 years, and I want to know the probability it's going to break down within that. So I'm looking for that. So I'm going normal CDF, and again here you could use a 0 or a -1E99. Either one is fine, only because I cannot have any data that's less than 0. I'm headed up to 2. I have a mean of 2.3 and a standard deviation of 4. And I'm going to type that in. And let's see, I'm doing infinity. And I'm going to 2 with a 2.3 and a 0.4. 22.663. So there's a 22.663% chance that this thing's going to break down, and it's guaranteed. Now, as owner of the Sunshine Stereo cassette, I'm interested in this data because that's how many, that's the percent of people who would be eligible for their money back. So I would either need to adjust my guarantee, maybe down to 1 year, or I need to fix my crappy stereo cassette deck, because 22% of them are going to break down within 2 years. Okay, we're going to take the exact same data, but we're going to convert it to z-scores. So what if we converted the Sunshine Radio problem to z-scores and used standard normal distribution? So before we were just using a normal distribution with our mean and our standard deviation. But if I standardize this, this is now 0, 1, 2, 3, -1, -2, -3. Always, always, always. And these have no units of measurement on them. Like that's not 1 hour, 2 hours. Okay, so it says, what's the likelihood that a Sunshine Radio will only last 450 hours? And so that's the second question on the problem above it. I want only 450 hours. Okay, so normally I would do normal CDF from negative infinity to 450. But if I'm doing a standard normal, I need to find out the z-score for 450 hours. So you're going to use that formula on the top back of your formula sheet. Standardized normal score. And then this is your data minus your mean over your standard deviation. So my information is a 450. The average was 600. And the standard deviation was 100. And take a second, type that into your calculator, make sure you're good typing that in. I got a -1.5. And feel free to pause the video. Anytime you need something to digest or process, or you need to slow down and write something down, please pause it, rewind it, do what you need to do so that you can go at your own pace. Okay, so this z-score is a -1.5, so I am here. Will only last 450, so I'm this. But when I do my normal CDF, I'm going from negative infinity to a -1.5, comma 0, comma 1. Guys, these are always going to be 0 and 1 when you're talking about a standard normal distribution. And then I'm going to go type that in. And I'm going to a -1.5 with a 0 and a 1. Okay, hold on. Try this again. No. -1.5. All right, I got 6.681. 6.681%. 6.681. And if I come back here, 6.681. for less than 450. You get the same exact answer, exact to 3 decimal places. So you can do this either way. Now, I know you're already thinking it. Why would I take the time to convert it to a z-score if I don't have to, if I can just do it the way we first did it? There's no reason. There's absolutely no reason unless you're on an FRQ and they say change it or using a standard normal distribution. So you just need to make sure that you can, and you need to make sure that you understand that they are the same. They are the same process. You are finding the same information. One is using the piece of data, and one is using its z-score. What is the likelihood that a sunshine radio will last more than 825 hours? I need to take this piece of information and turn it to a z-score. So 825 minus the average over 100. This one's going to be positive 2.25. So you're going to normal CDF from 2.25 to infinity, comma 0, comma 1. And then you're going to go type this sucker in. And let's see, we were 2.25 to infinity. Oh my goodness. Let's try that again. Um, 2.25 to infinity, comma 0, comma 1. And I got 1.222, which is, ta-da. Now, some of you, I hope, are thinking, do I need to go to infinity if, let's see, 68, 95, 99.7% of my data is within 3 standard deviations? What if, instead of going to infinity, I just went to 4? 4 standard deviations, surely that gets that last little bit. If 3 standard deviations gets 99.7, 4 standard deviations, surely that gets all of it. You know, sometimes it's probably going to be okay, and sometimes it's going to throw your data off a little bit. Let's see, this was 2.25. Let's go to 4. See how it's off? I mean, just ever so slightly, and well, 3 decimal places, it would change it because that would be 1.219, and the other one was at 1.222. So, moral of the story is, don't assume. You are so much safer if you will just start at negative infinity and go all the way to positive infinity, unless your data absolutely can't be negative, like this stuff. You'd be fine with starting at 0. But just, there's always this one freak radio that will last forever, or there's, you know, that one, you know, 10-pound rat. If you're doing the weight of rats in New York City, there's always this, you know, crazy, monstrous 10-pound rat that, you know, people talk about forever, and he lives out there, and so he is a piece of your data, and he's not going to fit within 4 standard deviations of your mean. So always account for the 10-pound rat. Moral of the story. Okay, so now we're going to do just a little bit of number crunching. I'm going to go kind of fast, and I'm not going to type these into my calculator. I'm going to tell you what your answer should be. I'm going to let you pause the video and type it in and make sure that you're getting it. So it says, let Z be a random variable with a standard normal distribution. That's important. Standard normal, that means I know I'm here. I want the area between 1 and 2.7. So I want all of this. So I'm going to do normal CDF from 1 to 2.7 with a mean of 0 and a standard deviation of 1 because I am a standard normal distribution. When you type that in, you get 0.155. If you want to turn that into a percent, that's fine. It'd be 15.5 something something percent. You're welcome to leave it as 0.155. It's totally fine. Just don't put a percent sign on it. Find the area to the right of 0.94. 0.94 is going to be about there. And I want to the right, so I want all of that. So I'm going normal CDF from here to infinity, comma 0, comma 1. Type that in. I got 0.174. So again, pause, type it in, make sure you're good. The next one, I want greater than 1.15, so I'm going to normal CDF 1.15 to infinity, comma 0, comma 1. And I'm going to get 0.125. Now, this is where it usually pops up. The question usually pops up. Okay, like this one has an equal to on it. So what if I gave you one that didn't? Okay, think about this. How close can you get to 1.15 without being 1.15? You can get infinitely close. So stats does not distinguish between does it have an equal to and does it not. Because this is a fluid curve, and these decimals can get, you know, as far as you want them to get. Like these decimals could go forever. So there is no difference between this and this when you type it in. Like if you don't see an equal to under here, you don't change this. Like don't go down a decimal or up a decimal, or throw a 0.9 on the end of it. Like it's treated exactly the same. I tell my kids, think about cutting a piece of cake. So think about this is the area of cake that you want. Well, if I cut it on this line, does that mean that that cake includes that line or not? Like you don't think about it like that. That's just where you're cutting the cake. I don't know if that made any sense or not. But that's how I think about it. Where you cut it, don't split hairs about the equal to and the not equal to. Okay. So for this one, Z is less than 0.025. So normal CDF, now this is less than. So I'm going from negative infinity to 0.25, comma 0, comma 1. Okay, common sense. Stop for just a second. How much should that be? I know that should be over 50%. Because from negative infinity to 0 is 50% of my data, and I'm just on the other side of 0 with a 0.25. And when you type this one in, you get 0.599. So again, make sure your answers make sense. This one is in between. So I'm going from negative 1.78 to 0.35, comma 0, comma 1. I got 0.599. Again, pause, type it in, make sure you're good. Okay, let X have a normal distribution with a mu of 10 and a sigma of 2. Find the probability that an X value selected at random from this distribution is between 11 and 14. And just for kicks, I want you to show with a normal distribution and a standard normal distribution. Okay, normal. I'm going to draw my curve. There's my curve. I have a mu of 10, standard deviation of 2. So he's a 12, he's a 14, he's an 8, he's a 6, just to give a couple. And I want between 11, so that's here, and 14 here. So it should definitely be less than 50%, but not by a whole bunch. So I'm going to go normal, CDF from 11 to 14 with my average and my standard deviation. I'm going to type that in, and I got 0.286. Now, if I go Z's, if I go standard normal, then all that changes 0, 1, 2, 3, -1, -2, -3. The area should stay the same, but what I type in is going to be different because I need to change these over to z-scores. 11 minus 10 over 2 and 14 minus 10 over 2. So that one's going to be a 1/2 and that one's going to be a 2. So I'm going to go from 1/2 to 2. Now what has changed? Your mean is now 0 and your standard deviation is 1. And I got 0.286. Pause, type it in, make sure you're good. That's a one really nice FRQ to show you both methods. Okay, now we're going to flip things around. What if I tell you how much area I have, and I want you to tell me what x value or z value on the curve would give me that much area? So to use that silly cake example I gave you, I'm telling you how much cake I want. I'm telling you the size of the slice. You have to figure out where to cut it. Okay? To do that, you're going to use inverse norm. Let me show you where that is. On your calculator, same place, just right there. And when you hit inverse norm, if you have the new operating system, it gives you area, your mu, and your sigma, and we're always going to be to the left. Inverse norm is always percent to the left. Inverse norm is always percent to the left. Inverse norm is always percent to the left. And then I just need my mean and my standard deviation. Okay, here we go. Magic Video Games Incorporated sells an expensive video computer games package. Because the package is so expensive, the company wants to advertise an impressive guarantee for the life expectancy of its computer control system. The guarantee policy will refund full purchase price if the computer fails during the guarantee period. The research department has done tests which show that the mean life for the computer is 30 months with a standard deviation of 4 months. The computer life is normally distributed. How long can the guarantee period be if management does not want to refund the purchase price of more than 7% of the Magic Video packages? Now you guys should be able to see exactly how this is used in real life. I can only afford to refund 7%. I don't want to refund 8%. I can only afford 7%. So think about your curve. And I really want to see a curve drawn on all these problems. Here's your average. And what was our average? 30 months. I only want to refund 7%. So if they die here, wherever here is, I don't know where here is, but I want this area to be 0.07. And I need to know where to cut this curve so that I only have 7% area here. Make sure that makes sense. Where should I cut it? What value does this need to be so that the area under this shaded part is 7%? So on this one, I know what the area is, but I don't know the x value that's going to give that to me. All right, I know mu is 30. I know I have a standard deviation of 4. Here's what I want. I want the probability of x to be less than 7%. So when you have the percent, you're going to inverse norm Percent to the left. Okay, well, here's my slice. A half percent to the left, so that's 0.07. And then I need my mean and my standard deviation. So when you do these, guys, I want to see your curve, and I want to see this. And I'm also, like, I'm just writing out what I'm given. I'm taking all this stuff that's in here, and I'm just writing it using statistics. So then I'm going to go distribution, and I'm going to go down to inverse norm. My area is going to be 0.07. I have a mean of 30 and a standard deviation of 4. $24.0968. Okay, now let me tell you about decimals. We have said since day one we're going 3 decimal places. They, the stats people, aren't crazy about zeros as your first decimal. They'll take zeros within the decimals, but they don't like 0 as your first decimal. So if 0 is your first decimal, we're going to go 3 more decimal places. So I'm going 4 total because I need 3 decimal places with meat on it. I don't like starting with a 0. So I'm going to go 24.0968. 24.0968. Now here's where people get real loosey-goosey with some terminology here, and they'll throw a percent on that. Is that 24%? No, it was 7%. It's 24.0968 months. So what have we just said? We have just said, okay, you can offer them a guarantee of about 2 years, 24.0968 months, and you should only have to refund 7% based on the data that we've gathered about how long these things last. So again, I used inverse norm because I gave you the percent and you were looking for where to slice it. I found this number. Okay. So now let's look at some just super basics. Find the z value so that 90% of the area under the standard normal curve lies between negative z and z. Okay, first of all, I'm not just a normal curve, I'm a standard normal curve. I need 90% of the area under the standard normal curve is going to be between negative z and z. Now, guys, I want this. This just means that these two numbers are the same. One's positive and one's negative. So my 90% is equally balanced. %. 90% of my data in the middle of this curve, and I want the z's that are going to cut off 90%. I want 90% of this cake, and I need you to tell me where to cut it. My z's are going to be the same. One's going to be positive and one's going to be negative. Well, remember, I know he's a 0 and he's a 1. What I don't know is the percent to the left. All right, think about this. If I want to find this guy, if from here to here is 90%, how much is the percent to the left? And it's not 10%. If from here to here is 90%, there is 10% left, but there's 10% that's got to go distributed evenly amongst both wings. So I've got to have 5% here and 5% here. So for this cut right here, I can only have 5% in here. So I'm going to go 0.05. All right, so I'm going to grab my calculator. I'm going to go, ooh, hello. I'm going to go inverse norm. let's see, we're going 0.05, 0, and 1 because we are a standard normal distribution. And that puts me at a negative 1.645. So he 0.645. Okay, now let's think about this for a second. This curve is symmetric, and my 90% is in the middle. So if this is a negative 1.645, shouldn't this be a positive 1.645? Okay, now for this one time, I'll prove it. Okay, percent to the left. Now I'm here. Okay, guys, how much area is to the left of that line right there? 95%. I got my 90, that's the piece of cake I'm going to eat. Then I got that 5% wing that's left. So I'm going 0.9501. And the point I'm trying to prove is that this number right here that we're getting ready to get is the same as that one right there. So I'm gonna, I'm gonna inverse norm 0.95. And I get positive 1.645. Moral of the story. A normal distribution is perfectly symmetrical. Perfectly symmetrical. So if I chop off 90% in the middle, my positive and negative z values are going to be identical. If one's a negative 1.645, the other one's a positive 1.645. If you went and found the positive one first, then you would just slap a negative on the other one. That will always, always, always be the case. Okay, this one says find the z value, so I know I'm a standard normal distribution, so that 3% of the area under the standard normal curve lies to the right of z. 3% to the right of z, I know I'm way over here. That's 3%. Now remember, inverse norm percent to the left. This is where I know I want to cut it. What percent is to the left? 97%. One 1.881. Suppose the time to complete a test is normally distributed with a mu of 40 minutes and a sigma of 5 minutes. After how many minutes can we expect all but about 3% of the test to be completed? Okay, draw your curve. I have a mean of 40 minutes. I want all but about 3%. That means all of these people, because this is minutes, this is in minutes. So all of these people are done. They're all done because they've all finished. So I want to know at what minutes can I chop it off so that all these people are done and these people are not. Now what did it say it wanted this percent to be? 3%. Well, if that's 3%, what's this over here? 97%. So I'm going to inverse norm, and inverse norm only does percent to the left. So 0.97 with my mean of 40 and my standard deviation of 5. Go type that in, and I got 49.5 minutes. Not a percent. 49 is not a percent. It's the number of minutes to where you can stop the test and have all but 3% done based on this data. On the driving range, Tiger Woods practices his swing with a particular club by hitting many, many balls. Suppose that when Tiger hits his driver, the distance the ball travels follows a normal distribution with a mean of 304 yards and a standard deviation of 8 yards. What percent of Tiger's drives travel at least 290 yards? Okay, now, get this right in your mind. Figure it out. Am I telling you where to cut the cake? And you're going to tell me how much cake you're cutting? Or am I telling you how big of a size of a piece I want, and you got to tell me where you got to cut it? If I ask for percent, you're a normal CDF. Normal CDF spits out probability. It spits out a percent. So I'm going to, let's see, we are 304 with a standard deviation of 8 yards. I want to be at least, not probability, I want the probability that X is greater than or equal to 290 yards. Okay, so 304, so 290 is down here. And at least means I'm headed that direction. So this should be over 50%. So I'm going to normal CDF, not 304, 290 to positive infinity, because you know it's Tiger Woods and we don't know how far he can hit it. You can have that one crazy drive that just goes crazy far with a mean of 304 and a standard deviation of 8. Pause it, type that in. And you should get 95.994%. What percent of Tiger's drives travel at least 290 yards? Almost 96% based on this data. If his average is 304. What percent of Tiger's drives travel between 305 and 325? Again, I'm telling you where to cut it, and I want what percent. So you're normal. You are a normal CDF from 305 to 325 with a 304 and an 8. And I got 44.593%. High levels of cholesterol in the blood increase the risk of heart disease. For 14-year-old boys, the distribution of blood cholesterol is approximately normal with a mean of 170 and a standard deviation of 30. What is the first quartile of the distribution of blood cholesterol? What is the first quartile? Well, that's the first 25%. Okay, now I'm asking. Am I asking you for a percent? Or am I asking you for the number that will chop off 25%? That's how you've got to attack all of these. So you know if you're going to do a normal CDF or an inverse norm. I'm telling you I want 25%. And I want to know where to chop it. So I know I'm an inverse norm. Percent to the left is going to be 0.25 with a mean of 170 and a standard deviation of 30. Pause this, go type it in. And you're at 149.765. I don't know what this is measured in. Blood cholesterol? Cholesterol level? All right, home stretch, but this one's a doozy. Let's make sure we read the question really carefully and make sure we understand what it's saying, because you're about to be a expert in trains. An important measure of the performance of a locomotive is its adhesion, the pulling force as a multiple of its weight. So its adhesion is the force. The adhesion of one 4,400 horsepower diesel locomotive varies in actual use according to a normal distribution with a mean of 0.37 and a standard deviation of 0.04. The locomotive needs to have an adhesion of at least 30% for the train to arrive on time, or a 0.30 for the train to arrive on time. If the adhesion is less than that, the train will be late because it doesn't have enough force to pull, so it'll be slow. An adhesion greater than 50 will result in the train arriving too early. Okay, now let's talk about this. If you have an adhesion, if you have this force greater than 0.50, then this thing is moving. It's horsepower, and it will result in their train arriving too early. Now, believe it or not, both are bad. Train schedules are very meticulous, and it's sort of like a domino effect. If one train is early or late, it can really throw off train schedules, not just at that terminal, but at terminals that they connect to. The locomotive's manufacturer is considering two changes that could reduce the percent of times that the train arrives late. One option is to increase the mean adhesion of the locomotive. The other possibility is to decrease the variability in adhesion from trip to trip. That is, to decrease the standard deviation. If the standard deviation remains at 0.04, to what value must the manufacturer change the mean adhesion of the locomotive to reduce its proportion of late arrivals to only 2% of the days? Okay, let's talk about what we were given. We want to be between, where is it? A point hold on. No. Here. Let's draw. All right. This is not time, this is force. This is the pulling force. If this is too strong, we arrive early. If the force is too weak, it doesn't pull as fast and we arrive late. But make sure that you're super clear that this curve is not time. This curve is force. Okay, we have a mean of 0.37 and a standard deviation of 0.04. And for lack of knowledge, I'm just going to put adhesion. Okay, now part A says, I want to change this. I want to change that so that I'm only late 2% of my days. So I want to know arrives late. I want this to be 2%. Okay, so if I know my percent, what are we doing? Are we normal CDF and are we doing an inverse norm? If you know your percent, you're doing an inverse norm. So I'm going to inverse norm 0.02. Now, here's the problem. I can't use this mean and this standard deviation. Well, I could use that standard deviation, but I can't use this mean because it's asking me to change the mean. So what could I use to find where to chop this off? Well, I could take this normal distribution and make it a standard normal distribution. If I do that, then I know that my mean is always 0 and my standard deviation is always 1. Now, this is going to spit out a z-score. Okay, so if I type this in, I get a z-score of a negative 2.0537. Notice I went 4 decimal places because my first one was a 0, and zeros suck. So I went 4 decimal places. So what I've just found is that I need to chop this sucker off at negative 2.0537 if this was 0, if that was my standard normal distribution. Okay, again, the question wanted the mean. I have a z-score. Do you have a formula that relates a z-score and a mean and I have a standard deviation? And you absolutely do. It's that guy. Okay, so here's the thing. I know him, just found him. I know him, he's sitting right there. I want him. The question is, who is that x? That x, let's go back and read. The locomotive needs to have an adhesion of at least a 0.3 for the train to arrive on time. If the adhesion is less than a 0.3, the train will be late. Okay, late. So what do I need this right here to be? I need it to be a 0.3 because it says the locomotive needs to have an adhesion of at least a 0.3 for the train to arrive on time. So that's my piece of x data. So I've got a negative 2.0537. I got a 0.3. I have an I don't know, and I'm going to change that to mu instead of x bar, over my standard deviation of a 0.04. I'm going to multiply both sides by a 0.04. I'm going to subtract the 0.3 over, and then I'm going to divide by -1, and I'm going to get a mu of 0.382. Now, I want you to pause right here and do that math and make sure you know how to solve and get that number. Don't miss this because you mess up on your Math 1 algebra. Take your time, go off to the side and go do that math and make sure you can get a mu of 0.382. Then stop and make sure you know where every number came from that got plugged into that formula. Okay, so I need to change my mu from a 0.37 to a 0.382 to only be late 2% of the days. All right, let's come down here. If my mean stays at 0.37, how can we change the standard deviation to ensure that the train will be late to only 2% of the time? Okay, well, I'm still 2% of the time. I still know his z-score. I'm still going to use this formula that relates all these suckers together. Sorry. So you can think of it like that, or you can think of it like that. Either way. This is if you have sample information, and this is if you have population information. This is x bar of a sample. This is the average of a population. Standard deviation of a sample, standard deviation of the population. Just don't interchange them. Okay, so I know that I want my mean to be 0.37. I know that I need to be a 0.3 for the adhesion to be good. I do not know the standard deviation, but I know that my z-score is a negative 2.0537 to fit the 2% part. So now to solve this, I'm going to subtract these two and get negative 0.07. I'm going to multiply both sides by sigma, and then I'm going to divide by the negative 2.0537, and I'm going to get that to be my new sigma. Okay, now let's look at part C. Which of the two options do you think is preferable? Now, I need you to be a train expert. Okay, here's what I wrote. We would prefer reducing the standard deviation. This would reduce the proportion of days the train is late and the number of days it arrives early. If we make mu larger, we will reduce the number of days it's late, but we will increase the number of days it's too early. So you have to stop, step back, and think about how these adjustments affect the big picture. Reducing your standard deviation reduces the variability across the line. But if you up your mu, it'll reduce the number of days that you're late, but it will increase the number of days that you're early. This is a fantastic FRQ. I know this is difficult. So the nice thing is you have this on video. You can read, you can redo it, you can just listen to it, you can try to write it from scratch, you can get a clean sheet of paper and start over. You do what you need to do, but I need you to be able to do problems like this. Okay. While experience can suggest whether or not a normal distribution is a reasonable model in a particular case, it is risky to assume that a distribution is normal without actually inspecting the data. The data should be roughly symmetrical, unimodal, bell-shaped, and a max and a min that should be about 3 standard deviations away from the mean. Not exactly, but about. Now, if you notice in all of these problems, it said this data follows a normal distribution. It states it up front. That's your go. That's your green light. If it doesn't say that, you need to inspect your data and say, assuming the data is normal, based on the data being roughly symmetrical, unimodal, bell-shaped, and that the max and the min are about 3 standard deviations away from the mean. 98% of the time, it's going to be normal. It's going to tell you that it's normal. But just be careful. A great multiple choice question could be, can I use a normal distribution to approximate this curve? And you just have to make sure that all these boxes are checked. Okay, so again, feel free to go back and just re-watch the notes now that you've written everything down. Go back to something you struggled with. Do what you need to do to make sure that you're good. And your job is to go finish all of the homework problems that you didn't do earlier. So whatever I assigned earlier, you need to go do all the other ones. Okay? And come into Smart Breakfast if you have questions.